Hi, my name is Steve Hoover. I'm the founder of Redwood EDA, and for the next hour, I'll be introducing you to transaction level Verilog. This presentation is from a verification perspective, so it's appropriate for verification engineers and folks who want to understand the general methodology of transaction level Verilog. So I'm going to start with a general methodology discussion and introduce transaction level design methodology as supported by transaction level Verilog. Then I'll give you guys a chance to get your feet wet with transaction level Verilog yourselves. We'll use the Makerchip Platform, which is an online IDE provided by Redwood EDA. After you try some simple things with transaction level Verilog, I will talk about concepts of transaction level design that are important from a verification perspective. We'll talk about pipelines, which introduce a notion of timing abstraction, which is valuable for simplifying the interfaces between your hardware models and your verification models by abstracting time. We'll talk about transactions, which similarly simplify the task of hooking up your verification models to your hardware models because the hardware models fundamentally understand what transactions are. And I'll define that a little clearer as we go in. And then, after talking through sort of the theoretical benefits, we'll talk about a case study where transaction level Verilog helps to create the verification harness that is used to verify a TL-Verilog RISC-V core generator. And you'll see that all of that modeling is done in a single page of TL-Verilog code. So looking at transaction level design methodology and where it fits in, transaction level design is in its very early stages of development. It's a methodology that's very forward-looking to the time when we're designing with trillions of transistors, excuse me, and beyond. So even today, register transfer level modeling is the predominant design methodology for new design starts. I think it's about 70% today. But RTL is really beyond its years and showing its age. The industry's been trying to get folks onto high-level synthesis for a long time and facing many obstacles with that. Transaction level design is geared toward addressing the shortcomings of both register transfer level modeling and high-level synthesis with C++ based modeling to support the next level of integration needs. This slide is depicting current design methodology, so a register transfer level design methodology, where the RTL model serves as our golden reference. For the most part, automated EDA tools take our design from RTL down to silicon. Transaction level design is elevating the abstraction level of our golden reference model, so the model that verification effort is targeted toward. And in addition to elevating the abstraction level for verification, it's also providing the mechanisms that are necessary for logic designers to express the implementation of that behavior at the register transfer level through correct by construction physical mappings. So expanding this view a little bit, we have our register transfer level model where all the verification energy is focused, and the verification infrastructure introduces various models at a higher level of abstraction that all need to monitor or connect in some way to the register transfer level model. Transaction level Verilog raises that abstraction level, which means not only is the verification effort simpler through abstraction, but also all of the maintenance of the verification models. Because the golden reference is at a higher abstraction level, and there's less effort to connect the higher level models to the transaction level. That simplifies the verification effort to associate these models through all the various changes that can happen over the course of the design process. So these correct by construction mappings help to absorb the physical churn of the model. They also enable various implementations of the overall behavior. So one model and one verification effort can be implemented in multiple different ways. Transaction level Verilog, transaction level design is not the only methodology that's being pursued as a follow on to RTL Design Methodology. So I just want to spend a little bit of time talking about various directions the industry is going. The EDA industry as a whole is very heavily focused on C++ based modeling and high-level synthesis of your C++ based models into silicon. So System C came about because of the desire, primarily the desire to integrate C++ based verification models with hardware modeling. And the idea of high-level synthesis, of course, is to take these higher-level models expressed as C++, essentially algorithms, into gate-level implementations in hardware. So essentially the magic red button that you can push that will turn your software magically into a faster hardware implementation. Obviously, that's a bit of an idealistic statement, but that's kind of the, where this vision comes from. The main focus of C++ based modeling with high-level synthesis today is technologies like OpenCL, where the goal is to enable one software program algorithm description OpenCL model to be implemented on various hardware platforms. So it can be running as software, it can be accelerated on a GPU, or it could be accelerated on an FPGA platform. Obviously, there's some customization that's necessary to do that, but all working toward this sort of ideal, where you've got one algorithmic description and very intelligent synthesis tools to map that to hardware. Academia is very much focused on domain-specific languages, and there's a long list of these. So pretty much every software developer who has learned hardware design has wanted to do so in the context of their favorite software language. So pretty much every software language out there has at least one domain-specific language for hardware modeling using that software. And this gives us, the benefit of more modern software techniques in the context of hardware design. And this is giving us better RTL languages. And then, of course, as I mentioned, transaction level design methodology. The idea is we're modeling hardware. And that sounds like a dumb statement. I mean, all of these languages should be modeling hardware, but all of these languages have software roots. Whether we're talking about RTL or C++ based high-level synthesis or DSLs, they're all derived from software methodology. RTL in particular is, Verilog came about as a language for verification modeling, as its name suggests, specifically for modeling event-based simulation of hardware behavior, not specifically hardware modeling. VHDL was more of a language for describing interfaces. So TL-Verilog is a language for modeling hardware, and it utilizes, as we saw, abstraction as context for design details. I've depicted sort of the documentation behind all these technologies. You've got industry tools which are very complex, have a lot of legacy behind them, many manuals to get through to really master the art. Academia layered on top of software languages, which are well documented, but introducing hardware support that's, as you would expect from academia, not always the best documented. It varies. And transaction level modeling, where a few very simple constructs, some of them you'll learn today, some you won't, layer on top of existing languages, Verilog in particular, and really obviate the need for a lot of the Verilog language specifications. So this sort of faint stack of documents would be the Verilog documents that you don't need so much anymore. Mainly you need the language extension, which is a very short document. I think the specification currently is about 12 pages, and it'll grow over time as the language matures, but very capable language today with very little documentation. So transaction level Verilog in particular, the specific implementation today, it's implemented as an extension to System Verilog. So it's really just extending your existing System Verilog environment with better capabilities. You can begin uh, utilizing those capabilities incrementally without disruption to your existing environment. Along the way, it's eliminating a lot of the baggage that you need to understand to develop using Verilog or System Verilog. So things like generate blocks and the notorious blocking versus non-blocking assignments, packed versus unpacked data types, and the various restrictions around when you can where you can use what. Always block, sensitivity lists, reg versus wire versus logic versus bit. None of these concepts that are more sort of legacy about the modeling methodology behind Verilog, no longer relevant with transaction level Verilog. TL-Verilog, the initial focus is on supporting designers, and verification engineers will benefit through designers using TL-Verilog. We'll also talk today about benefits that verification can experience from doing verification modeling in transaction level Verilog. And there's also a very strong benefit from modeling HLMs in a way that's synthesizable. So obviously everything in transaction level Verilog is synthesizable constructs. It's not only a good language for doing high-level modeling, but it's one that's fully synthesizable. And that means you can target your verification modeling to hardware acceleration on hardware emulators. Okay, so time to get your feet wet a little. I'll spend about a minute introducing the Makerchip platform, and then you can try it out for yourselves. So let me pull up Makerchip. So I'm going to go to, I guess I can't do that yet. I'm going to go to makerchip.com. So open up the IDE, and we'll wait a couple seconds for this to load. So Makerchip is a full IDE for front-end development of your hardware models, and it has support for transaction level Verilog. I'll open up a design that we can play around with. All right, so obviously you've got your editing window where you can enter your hardware logic. You can compile that logic here, and that's going to generate a logic diagram. It's also going to run hardware simulation on the server, and you'll get a waveform back that you can use to debug your design. We can highlight elements in the logic diagram. And I'm going to put the waveform down in a separate view here. The elements that we highlight on the logic diagram also are highlighted in our waveform. Fairly primitive waveform viewer, but the integration with the other elements of the design environment, the ability to highlight signals in the waveform, the fact that the signals are presented in a way that's organized by the hierarchy that TL-Verilog introduces, is very valuable in the debug process. The signals that I highlight also highlight in this nav-TLV representation of our code. So this should look very much like the code in our editor, but this is the understanding of our code that the tools have. And here's where you'll get highlighting of error conditions, values used, but it's never assigned. And as we highlight signals in the various views here, they highlight in our code here as well. So nice tight integration. As you find an issue in your waveform, something looks suspicious, you highlight the signal, get a diagram representation, trace it back to your source code. You can click on a line number to jump back here, and the line's highlighted, edit, solve it. Okay, so I'm going to give you guys a chance now to play around with that on your own. So we'll get rid of this window, and so your first lab exercise here is just to get familiar with the Makerchip platform. You can go to makerchip.com yourselves. And this lab exercise, the challenge here is simply to reproduce this window. So split windows, move tabs around, highlight signals, play around with the environment. And I will let you pause the video while you do that. And when you're ready, you can start up the video again. And we've got another 2 quick labs that you can do inside the Makerchip platform. Okay, so now that you're familiar with the Makerchip platform, the next lab exercise is just a quick lab exercise to let you code some very simple combinational logic, essentially some logic gates, starting off with an inverter with this expression here. And then you can try some simple logic gates. And you can see in the in Makerchip how these logic gates simulate, view the waveforms, view the logic diagram, play around with the platform. Make sure you're using 3 spaces of indentation as you code this logic. And again, I will let you pause the video and try this out for your own and start up when you're ready. All right, the next lab exercise just goes beyond gates to vectors, where you can do some arithmetic. So instead of trying out simple logic gates, you can try doing an addition. Again, the lab's pretty self-explanatory. You can stop the video now and start up again when you're ready. Okay, so now that you've played around with some simple things inside Makerchip, I'll introduce the first new concept in the language, which is pipelines. Pipelines is typically a concept that you learn later in the logic design curriculum. In transaction level Verilog, pipelines are a very fundamental notion. So in this example, we're going to look at a pipelined computation of Pythagoras' theorem. So we're computing the distance in this triangle C from the distance of the legs A and B. So as we learned in school, the distance C is the square root of A squared plus B squared. And we're going to implement that by first squaring A, squaring B, and then we're going to add those together and take the square root, and that's the implementation of our formula in hardware. I have staged this along through flip-flops. So this is a fairly deep computation at a reasonable clock speed. We're not likely to be able to perform this calculation within the clock period, so we need to distribute the computation over multiple clock stages. And so we're going to stretch it out over 3 stages in this case. If you're not familiar with flip-flops, if you're not familiar with pipelines, you might want to pause the video and do a little bit of Googling. I'm going to assume a basic level of familiarity. So now going from our sort of RTL mentality view of this logic, I'm going to take that to a timing abstract view of the logic. So we're going to put this logic in the context of a pipeline, and the pipeline has 3 pipeline stages. And putting the logic in that context, we no longer have to draw the flip-flops. The flip-flops can be implied from the context of the pipeline. So wherever signals need to cross stage boundaries, that implies a flip-flop. The transaction level Verilog representation of this pipeline is a very direct map between what you see in the picture and what you see in the code. We have a calc pipeline. It's got stages 1, 2, 3, and logic within those stages. Comparing versus System Verilog, we get a nice code reduction from doing this. You can represent your logic in Verilog many different ways. This is one of the recommended industry practices, and we see a nice code reduction. More to the point of transaction level Verilog, the code reduction is nice, but it's really about the separation of how we distribute our logic in the pipeline from the behavior, the logic that's performed by the pipeline. In particular, in this scenario, we're looking at the need to repipeline our logic, retime our logic. So let's say we're putting this logic in the context where maybe AA is available on one corner of our silicon, and we need CC in the other corner of our silicon. And that means we need a lot of dead time just for transit. So we decide on this implementation, and we can get from the first implementation to this implementation just by changing the stage designations around this logic. What's important to note here is that the stage designations are a form of mapping. Okay, they are not an expression of the behavior of our model. They're an expression of how we choose to implement that behavior. Going back to our earlier picture, essentially these ats are a form of mapping. And they're the main one that we're going to focus on today. They're primarily the one that's supported by current tools. As transaction level Verilog evolves, there are other forms of mapping coming down the pipeline. Today, this is primarily it, which gives you a timing abstract representation of your design. Looking at this example in the context of the Verilog, system Verilog model, a retiming change like we're looking at is very disruptive to the code, very bug prone, whereas it's very safe in TL-Verilog. Now you get a chance to try this for yourselves. So this example, just to set context for it, I'm assuming we have some pipeline computation like the Pythagoras' theorem computation. And that computation is resulting in a number of error conditions. So here I'm depicting bad input, illegal operation, overflow, divide by zero, whatever these conditions happen to be. We're not concerned with the actual computation. You're going to create the logic that takes these error conditions and accumulates them, resulting in a single, in this case, the signal is called error 3, a single indication that there was an error. So this is just ORing up the various error conditions as they march through the pipeline. So you're going to create 3 logic expressions in appropriate context for these ORs, ORing these error conditions together. I have given you, for reference, the Pythagoras' theorem example, just sort of a syntax reference. Again, note that indentation is 3 spaces. As you've seen, there's no explicit begin end. It's like Python, it's based on indentation, and in TL-Verilog that must be 3 spaces. The OR operator is vertical bars, and at this point I'm going to let you work through this exercise, and you can stop the video now and restart when you're ready to continue. Okay, so I hope that exercise went well and you were able to create your own pipelined logic. We're going to look at one more pipelined example. This example I'm introducing so that we can get into verification benefits. This example is one that I took from somebody's blog post where they were talking about how you can implement a multiply operation on an FPGA. So an FPGA fundamentally supports a multiply accumulate logic block, or a DSP block, and that block supports an 18-bit multiply operation. So here we're implementing a multiply using these MAX or DSP blocks to implement a wider multiply. So I think here we're implementing a 35-bit multiply, if I'm not mistaken, um, which is essentially two 18-bit multiplies. So to implement this using the narrower multiply, 18-bit multiply, we have to divide up the multiply operation and do a partial products multiplication. So this is very similar to the way we learned long multiplication in school. We have two numbers that are broken into two fields. So in long multiplication, these would be our digits. Here, they're the two halves of the binary numbers. And we need to do all permutations of multiplying these two fields. So those permutations are labeled PP1, PP2, PP3, PP4, partial product. And we need to multiply them and add them together. And the blog post is proposing an implementation where in each stage of the computation, you're doing a multiply accumulate. Actually, I think the multiply accumulate is multiply in one stage, accumulate or add in the next stage. And each cycle of the pipeline, they're doing another multiply and accumulating that partial product into the result. And this is the resulting implementation in logic diagram from Makerchip in TL-Verilog. The blog post was in VHDL. This is the original on the right and the corresponding transaction level Verilog. So again, we can see a very nice code reduction from logic that's a very natural pipeline. So the point of this exercise is to introduce verification concepts and the benefits of transaction level Verilog for verification. So typically in verification, you'll have your DUT, which in this case is our multiply logic. And your test bench is monitoring the behavior of that DUT. It's monitoring the inputs and checking the outputs. So in this case, our check is just to do the wide multiply A and B, and make sure the output is that multiplication. Of course, here we have a 6-stage pipeline, so the inputs are early, and we have to deal with the stages. TL-Verilog, of course, is very convenient for doing that. This is the test bench coded in transaction level Verilog. So we'll give ourselves a test bench. It's going to have a mul pipeline just like our DUT. We're going to get our inputs in stage 0 of the pipeline, and these statements are just reaching from the test bench context into the DUT context to grab the AA and BB signals. And then in stage 6, once we've got our multiply result, we're going to check it. So we're again reaching into the DUT for the multiply that's coming out, and we're making sure that it is indeed A times B. I can simplify this a little bit further, and we'll talk about this construct more later. But just to point out, the example can be a little bit simpler. In place of individually grabbing A and B from the DUT into the test bench, we can use this more generic mechanism to grab any signal from the DUT, put it in the test bench. Different ways to skin a cat. Instead of creating separate context for our test bench, we could just put our assertion in place. So in System Verilog, with System Verilog assertions, I'm not sure where System Verilog ends and System Verilog assertions begin, but sorry. But after about an hour of Googling around, I managed to find this syntax for reaching 6 cycles into the past to grab the Verilog signal for A, and 6 cycles into the past for B, and then doing this check to do a nice compact assertion in System Verilog. Correspondingly, in transaction level Verilog, since you have the context of a pipeline, that eliminates the need to explicitly reach back 6 cycles. You simply reference A in cycle 6, and that implicitly requires 6 stages of staging. So more than just simplifying the assertion, you'll note that the TL-Verilog assertion remains valid if we were to stretch this pipeline, right? If we change our DUT so it's a 7-stage pipeline instead of 6, or all compacted into 2 stages, it doesn't matter. It's the same assertion statement. System Verilog also gives you a mechanism to create a test bench that you link with your DUT logic. So you can create a separate test bench in a bind file, and that test bench will have its own interface with explicit interface signals and explicit hookup of those signals. In this case, the explicit hookup is using the wildcard expression because I'm using the same names. But you've got an explicit module interface with an assertion. I didn't test this logic, and I'm not an expert in creating bound test benches in Verilog, but this is what I came up with. In TL-Verilog, you can do something similar to isolate your test bench logic as it's structured in the code. You can create a macro, and in this case, I am defining a macro that reaches directly into the DUT logic to drop this assertion in place, which is something that System Verilog does not allow you to do. Taking this one step further to a domain that's actually not supported yet in transaction level Verilog, but it's worth having kind of a heads up where this is headed. Instead of expressing this as a test bench that is explicitly verifying the behavior of your hardware model, we express this as alternate representations of the same behavior. And this is made up syntax I put on the slide just to convey the concept. The syntax is not solidified, but the notion here is that you have your physical implementation. That's the design that we looked at already. And then you have your alternate expression of that logic, which is your wider multiply in this case. The only real distinction here is that we're not explicitly comparing the outputs. That it comes implicitly from the fact that these are alternate representations. So the infrastructure can know to drive the inputs to both of these and to compare the outputs. The main benefit of doing this now is that, in this case, we saved ourselves writing an equals equals. But one of the core benefits of doing this is that we've isolated this verification problem. And once we've proven that the simpler representation is the same behavior, we can now replace the more complicated physical implementation with this more abstract representation in our broader simulations of the full chip or whatever higher level simulation. And that will speed up our simulations and simplify our higher level modeling. I won't go too far down that path since that's not currently implemented, but I wanted to give you a taste. Since we're focused in this presentation on verification, there are concepts that are more relevant to hardware design that we're not going to talk about. I just want to tell you what those are. If you do want to learn more about these, you can find other training material online, like a webinar that I gave on Udemy. Transaction level Verilog has an explicit construct for state. It has the ability for the designer to convey in the model when computations have meaning and when they are just a bunch of logic gates doing what they randomly do. Validity is a useful concept for verification. It's good for your verification interfaces to understand when there's a valid transaction. But in the interest of time, I'm not going to dive into that one in this presentation. Pipeline interactions, so, and we've looked at a very simple pipeline, but in the real world, you have interactions between pipelines, you have feedback paths, feed forward paths, bypasses, prediction paths, and so on. These are all easy to model in TL-Verilog, but we won't go into that. And TL-Verilog also introduces a convenient construct for design hierarchy, which replaces multiple forms of design hierarchy in Verilog. So next, we're going to take things from free-flowing pipelines to more arbitrary microarchitectural flows. So in a free-flowing pipeline, you have in the simple case, one transaction flowing through the pipeline, every cycle going to the next stage. Now we'll start looking at transactions which follow different paths. So this example is going to use our same Pythagoras' theorem example, but instead of implementing that in a free-flowing pipeline, we're going to now transition that implementation to a stall pipeline. So what do we need to do to introduce stall into our pipeline? First, we need the ability to hold on to the values in our flip-flops. And we could represent that two ways. One, as I've done here, is to explicitly recirculate the value through a mux. The other would be to control the clock that controls the flip-flops, which inherently are capable of holding values. Logic synthesis tools are able to easily transition from one implementation to the other. It doesn't really matter how we represent these in our model. In a transaction level Verilog mindset, I prefer to think of these as recirculations. And then we need to add our stall signal, which controls the recirculation. So taking this logic diagram and literally translating that to transaction level Verilog, well, first putting this in, depicting this in transaction level Verilog mentality, we now have to break our pipeline because we're no longer free flowing. So we've got two recirculation points, which break our pipeline into three. So now we have these mini sort of degenerate pipelines. And we no longer have to draw our flops explicitly. Where I've recirculated the values outside of the pipeline context, there's no implied flip-flop. Where they're crossing stage boundaries inside the pipeline, that implies a flip-flop. So literally taking this diagram and expressing it in logic, you would end up with this. I'm going to do a couple transformations on this code. So first of all, these lines here with a squared and b squared that are recirculating a squared and b squared through these recirculation muxes. I'm going to code these more generically as recirculating any values. So instead of explicitly recirculating a and b squared, I'm going to say that any signals that we need in the first stage of the Calc2 pipeline, we can get by recirculating that value through a mux and pulling from the Calc1 pipeline. I've done the same thing for this recirculation mux for the Calc3 pipeline. Now that I've expressed things in a more generic way, I'm going to take those generic statements and elevate them to the top. So now everything at the top is a generic expression of a stall pipeline. Okay, these first 6 lines, I guess it is, say nothing about the computation that we're performing. They are expressing the stall behavior. So now that I've taken this generic stall behavior and isolated it, I can put that all into a library component. So there's an evolving library of flow components for transaction level Verilog, and it contains a stall pipeline macro. So we can just instantiate that macro. This is something you can't do in RTL because RTL doesn't give you the ability to sort of reach into context established by a module and add additional logic into it. So now, just compacting this code a little bit, now we're at the point where we have an expression of our logic that looks very similar to our original free-flowing pipeline expression. We say we want to stall a pipeline, and we add in that into that context the combinational logic expressions. Combinational logic expressions don't change at all. They're just put in new context. Okay, so that was a simple stall flow. As I mentioned, there's a library of flow components, and we can use that library to construct a more interesting flow. So in this example, it's a somewhat contrived flow just representing various types of flow components. And we can construct this flow out of the library macro instantiations very briefly. And then add transaction logic into the context established through these macro instantiations. So logic like decoding packet headers and performing instruction decode, whatever we might be doing. That can all be added then into this context. And I can show you so I'm jumping over now to Makerchip to show you this example, or very close to this example. So this is one of the examples. If you go to tutorials, examples, that pulls up this, this pane. And the example that we're looking at is the transaction flow example. So this is very close to what we were just looking at in the slides. And I've compiled it already. And you can see the logic diagram. Just for fun, I'll kick off the compilation again. You can see it churn. But while it does, we can look at this flow that I've already generated. And you can see that we've got a test bench that is producing transactions that now feed into our .dot logic. And we started off with a stall pipeline. And you can see the transaction flowing through the pipeline stages of the stall pipeline. Then it goes through a FIFO, which is in the stall 2 pipeline here. And we're going through I think a back pressured pipeline here into the ring. So I think here we're entering the arbiter. This is the bypass through the arbiter. And I believe this is the path that feeds into the ring. So this is actually down here, this is the ring itself. So these are the pipelines that exist in every hop of the ring. And then we hop out of the ring into this ring out pipeline through the arbiter. I don't have the queue in this particular example. Out of FIFO and back into our test bench. We can also, just to kind of explore this model a little bit more, we can explore into the ring stops of our design. And so this is inside the ring itself, and see the transaction passing through. Okay. Okay, so back to the slides. So we saw a ring example inside Makerchip, and we have combinational logic within that example that we can then map into context. Similar to what we saw with our free-flowing pipeline, in our free-flowing pipeline, if we ask ourselves what flip-flops do we need between particular stages in our pipeline, the answer is anything produced on the left and consumed on the right, we need to flop forward. And that same kind of concept applies to our transaction flow as well. So if we ask ourselves what needs to flow through this FIFO, the answer is anything produced on the left of it and consumed on the right of it. If, for example, we have a timing issue with some logic on the right side of the FIFO, maybe this combinational logic here is just an AND gate, and it's a critical timing path, so we decide to alleviate the timing by moving that AND gate to the other side of the FIFO. We just drop it into a different context. Oops. Move it to the stall pipeline and let the tools manage the fact that now it's different information that needs to carry through the FIFO. So, a more realistic scenario where TL-Verilog tools are doing a significant amount of work for us. Let's say this microarchitecture is reasonably well implemented at this point, and we're looking to implement this in silicon. And our reliability team comes back to us and says, we got a problem. We've got too high an error rate, and we need to get the error rate down for the FIFO and the ring. And our architects decide to address this by adding parity to the FIFO and the ring. And we do that by adding a parity computation before the FIFO. We carry that parity bit through the FIFO, through all of these microarchitectural constructs through the ring. Instead of checking parity after the ring, we're going to carry that parity forward through the arbiter so that we can cover both the parity in the FIFO and in the ring in one check. So at this point, we'll check parity by doing also by doing this, we cover these two additional structures, which doesn't hurt. So the parity check is basically recomputing parity and making sure the parity matches the new computation. If it doesn't, there was a bit flip. And through the magic of transaction level Verilog, we can implement all of this just by adding these two statements for the parity and the parity error check. The tools will recognize that parity is consumed here and that it can be found back through this transaction flow. So chasing the graph produced by all of these any expressions back through this flow to the point where parity is available, and then dragging it, stitching it forward through the logic. So two very simple lines of TL-Verilog code resulting in hundreds of lines of RTL change. So we've been looking at logic design in transaction level Verilog. Let's now again look at implications for verification. So essentially the design that we were looking at is a router. We can view that router as a black box. Transactions go in, transactions come out. If we need to create a test bench for this router, we need to look at the transactions coming out and make sure that they're consistent with the transaction that was sent in. Maybe do some ordering checks on the transactions, verify the fields of the transactions versus what was sent in, things like that. In order to do that, we will need to hold on to the instructions that we saw going into the router so that when they come out, we can look them up. So we'll create ourselves an in-flight table. When transactions go into the router, we'll stick them in the in-flight table as well. And then when transactions come out, we have to find them in the in-flight table and do whatever checks are appropriate. So one of the challenges here is knowing when we see something come out, what it matches up with going in. Very likely the packet or flit coming out doesn't have an identifying field, and might not have an ID. So we might have to build, depending on the nature of this router and the nature of the fields that are available at the output of the router, some fairly sophisticated heuristics to deduce what that what that correlation is. Transaction level Verilog gives us a nice opportunity to solve that problem. So assuming that the router was modeled where there is a transaction flow full way from input to output, the solution is just to add an ID field. Nothing complex. We just add an ID, which is probably just the index into this in-flight table, and then when the transaction pops out, our check is going to use that ID and look up the instruction. So we're using this ID to put an additional constraint on our checking, that we're only going to check the scenario where this traffic coming out, this ID does indeed identify the right transaction. And because it's an additional constraint, we're not introducing any false positives by utilizing this information. All right, so back in Makerchip, just to relate this to our code, we can, so in the example that you'll find in this examples tab here, which I've loaded, the test bench is also hiding in a macro. It does not have an ID field. Let me just show the code in its entirety here. So this is the complete code for essentially the microarchitecture that we were just looking at. It's all macro instantiations that stitch together based on the arguments that are provided. And then we have our test bench, which is also a macro, because the test bench itself is generically a test bench for routers, whether they're ring or whatever topology that router might be. And this logic I've just added in for this presentation to show how we would add that ID field. So if we were to do this in the context of the test bench, we don't need to provide these context lines, but these lines are putting us into the right context. So this is the context in the test bench that is generating our transactions. And so we're going to have our transaction now generate an additional ID field. And this is a print statement of the transaction ID that we're sending in, and another print statement of the transaction as it's coming out. So this is in the context where the test bench is receiving a transaction from the DUT. And we see in the gen trans, we see an ID field now. So we can see there's a transaction coming in. And I can go into, so this transaction, we look at the log. This would be this transaction, which is also this, and it's destined for destination 3, ring stop 3. So I'm going to go into the ring stop 3 where it's received. And we see the ID field. So zooming in, and let's highlight both. So the ID of 7 here coming in. We see a transaction with ID C7, and looking a little bit further in the trace, we see our 7. All right, so I'm going to jump back to the presentation. If you'd like to try this for yourself, you can follow these instructions here. All right, so now I'm moving on to Warp 5. So real world sort of example of where the verification benefits come into play. So Warp 5 is a CPU core generator written in TL-Verilog. It can be a RISC-V core, it can be a MIPS core. It's highly configurable, especially in terms of the pipeline depth, where obviously TL-Verilog plays a big role in helping to support different implementations at different pipeline depths. So, excuse me. So support for advanced language features in transaction level Verilog is currently supported in sort of a proof of concept implementation using a macro preprocessor called M4. Over time, these capabilities will be more natively incorporated into transaction level Verilog itself, but we're taking the time to explore these features before hardening them a bit in the language specification by using a macro preprocessor. So, the model is parameterized even to the extent of configuring the ISA that we're implementing in our CPU. You can choose different branch predictors, and then you can parameterize the pipeline staging to get different depth pipelines in our CPU. So that all gets collected up through macro processing, preprocessing, and passed along as transaction level Verilog. Everywhere in the prior examples, you saw macros with the name M4, either M4 underscore or M4 plus. That's because it was going through the macro preprocessing step. And then the transaction level Verilog, of course, is turned into Verilog with all of its flip-flops and hierarchy and so on. So we can implement a simple microcontroller at a slow clock frequency with a single stage pipeline, or we can implement a deeper pipeline implementation, reasonably with this model, 7-stage pipeline, or a little deeper if we've got more memory latency is reasonable. This is a pretty textbook microarchitecture. Single scalar, meaning it's processing one instruction per cycle. More generically, WAR5 is a variable stage implementation, and then through M4 macro or M4 definitions, we identify which of these stages, potential stage boundaries, is going to be a real stage boundary in the implementation. So, focusing on the aspects of this model that are relevant to the verification problem. For the most part, the CPU pipeline is just a free-flowing pipeline, so a very straightforward, pipeline construct in TL-Verilog. Memory, however, it's WARP5 is written to support a variable latency memory access, and in fact, an out-of-order memory access. The memory is implemented to be in order and fixed pipeline latency, but it's set up to support variable latency out of order. So load instructions travel through the main pipeline and then issue out to the memory pipeline, and sometime later come back into the main pipeline in order to write their result back into the register file. And there's some complexity in the CPU pipeline to reserve a slot for this write back. But as far as the verification is concerned, what's relevant is that we have this path through memory that needs to come back to write the register result. So our verification challenge now, we have a verification infrastructure called RISC-V formal. And this framework is a bunch of verification checks to verify that our implementation is, in fact, a valid RISC-V implementation. And we need to feed this RISC-V formal infrastructure with instructions one at a time. So we need to provide it for each instruction that retires in our CPU, feed that instruction into the checks. So all the relevant fields of the instruction, the PC, the actual instruction in its binary form, the register values that it's operating on, the resulting register value written back to which destination register. So all these fields need to be presented in the same cycle to the checking. RISC-V formal does support the ability to have these instructions presented out of order. So that's convenient for us because our loads need to go through memory before we can present them. So we hook this up such that the majority of instructions, when they reach the write back stage of the pipeline, are presented to RISC-V formal. Loads, however, will be presented once they've come back from memory, because only then do we have the load value from memory that needs to be presented along with the rest of the instruction fields. So transaction level Verilog now and transaction flow is very important for, as well as timing abstraction, to help us create this test harness. So by test harness, I mean everything in red except for risk-B formal. So that's all of the connections to the various fields of the instructions throughout the pipeline, gathering them up and presenting them to the checking. And then for transaction flow, we could take two different approaches. One would be at the end of this pipeline to store off in a storage structure all the fields of the instruction that are relevant, and then when the data comes back from memory, look that up and present it to risk-B formal. In our case, with transaction level Verilog modeled as a transaction flow, it's very easy for us to just take advantage of that flow and let the fields of the instruction carry forward with that flow along with the instruction through memory to be available to present to the checks. So as promised, all of this test harness is created in a single page of code supporting all the variable pipeline depth implementations of RISC-V. The first couple lines here are the MUX. Then there are a couple lines of combinational logic that's providing information that needs to be presented to the checking that's not inherently already available as a signal in the hardware. And the rest of it, more than half is just the hookup of the risk-V formal Verilog signals to their TL-Verilog counterparts, in some cases with some combinational logic. So that's the entirety of the test harness. Essentially, all these red flows and connections to signals, that all comes for free. We just need to code the MUX and present the combinational logic that's necessary to present the proper information about the instructions to the checks. So a little bit of data about these. So what we're representing here, the bar on the left is the transaction level Verilog source before M4 preprocessing. Then that goes through M4. And we're representing here characters of code, excluding white space and comments. So the transaction level Verilog source goes through macro preprocessing to generate pure TL Verilog code. And that's broken up here by the DUT logic and the test harness. So this bar here is our one page of code. That TL Verilog gets processed into system Verilog. I've colored the bars here. And you can see that we get signal declarations in the Verilog and staging logic in yellow. This is a one-stage implementation, so there's not much staging. Looking at other implementations, a 5-stage and a 7-stage, you can see that the transaction level Verilog logic looks almost identical. Not only is it the same amount of code, it's almost the same code, basically. It's the at designations, for the most part, that are different. And likewise, the test harness is the same. The Verilog logic, on the other hand, not only can you see that the bars are growing, but even though the bars are the same size, the actual code is very different. And that's mainly because any sane signal naming methodology in Verilog or system Verilog is going to reflect the pipeline stage in the signal name. So all of the occurrences of that signal name, well, not just the pipeline stage, but also the scope is reflected in the signal names, where in transaction level Verilog it's not. And you'll see as the pipeline gets deeper and deeper, the bars grow, in particular the staging logic, as well as the signal declarations, as you would expect. So from this single pool of source code, with implementing a highly parameterizable CPU core generator, or parameterized, I should say, we're able to generate all of these different implementations, and the size of the implementations is growing very significantly. So in essence, you could compare the source, one single source versus all the various Verilog that you would have to write by hand if you were using a Verilog-based methodology. So summarizing what we've learned today, TL-Verilog models are easier to verify because the designs have fewer bugs, less code, fewer bugs, and the more complex parts of your code are now able to be provided through macro libraries, generic macro libraries. In a Verilog-based methodology, it's impossible to provide generic components for things like a stall pipeline, because Verilog is sort of a black box methodology. Everything inside that black box has to be part of the macro or module, whatever the library component may be. In TL-Verilog, that's not the case. We saw that, in particular from WAR 5, that the test harness development can be highly automated. We saw that verification models remain valid through various design changes, in particular timing changes. And we saw that TL-Verilog, is also good as a verification modeling language because, as I mentioned, it's 100% synthesizable. And also you have the same language, tools, environment for both the verification modeling and the hardware modeling, using a language that's more appropriate for hardware modeling versus the System C approach of using C++, which is fundamentally a software language. All right, so that's it for today's presentation. Feel free to explore Makerchip further. As you saw, there are tutorials available in Makerchip and some other learning materials. There are links to projects that have used Makerchip, first-class infrastructure for deploying logic in cloud FPGAs. You can incorporate this logic as microservices as part of accelerating web and cloud applications. So there's some various things you can explore and further presentations and material that you can find inside Makerchip. Thanks for participating.